So it's important to motivate why we study concept learning in the first place. This is an algorithm that's actually practically useless because of certain assumptions that it makes. But it is a very simple algorithm, and it makes it very easy to understand very important general concepts in machine learning, certain issues about the hypothesis space, and how to go about learning and searching through all the possible possibilities of the concepts. Okay, it is a white box model, which means it is the prediction is going to be interpretable and explainable, and it actually relates very well to previous coursework that you should have taken as a prerequisite to this course. So, for example, your discrete math class and the principles of logic and search that you've hopefully already learned or are learning in conjunction with this in Foundations of AI. So you're going to see that this is an algorithm that is principled, and because of that, we're going to see a couple of proofs on concept learning.
So for the enjoy drink concept, we're basically going to have to put things into a positive bucket or a negative bucket based on whether we think our friend enjoys the drink or not. And there are lots of different ways that the people in machine learning denote positive and negative classes. So you'll see sometimes the notation with the plus and minus sign with the VE at the end, or without, so plus or minus. We can also use numbers, of course, so we can say anything above 0 indicates a positive class, so a positive 1 is the unit value for that, or negative 1 for the unit value in the negative space. Or because they're, Boolean digits, we can use binary digits, we can use the numbers 1 and 0. And because of this particular case being whether somebody enjoys the drink or not, we can say that they truly enjoy the drink or they don't. Okay, so basically we're going to take data instances. So for example, this one which you have in your slide here, sweet local coffee, or kopi as you would call it in the canteen or the kopitiam, the food court. Basically this drink has condensed milk, water, and coffee, and the coffee is sweetened with some extra sugar. The condensed milk is also somewhat sugary, so this is our sweet local coffee. And if we were to turn to the back of this, then we would say, okay, we're going to describe that particular drink as having certain attribute values. So our drink is coffee, that's what is specified. Our milk, sugar, ice, and strength we didn't mention. Those are particular value attributes that we've set. As we'll see later, we don't take all of these values, especially we're not going to talk about the sugar as being blank. It's either going to be extra sugar or no sugar at all. Okay, and we've also set the final attribute as having here, so living, which means to drink. Okay, we're going to say this is a positive instance, right? We can get another drink and ask our friend whether they like it or not either. Okay, so here we have another one. This is coffee bing, or iced coffee, and it's the same as the coffee one, except it differs only in one attribute, right? The attribute of having ice or not. That's the only difference here. Okay, and so let's say our friend says both of these drinks are positive instances, so that's great. And we might get some negative instances as well. So let's say our third drink that we get here is sweet local tea, and let's say our friend doesn't prefer that, so they'll put it in the negative space. Okay, so based on this type of data, we're going to try to train our system, our concept learning algorithm, to recover what type of function f our learner likes, our target concept likes, sorry. Okay, and when after we've done that learning, we can ask the model, okay, whether a drink is preferred or not. So let's say we get another drink, kopi o kosong, and we can decide using the hypothesis space that we've learned whether it belongs either in the positive instance or the negative instance. Okay, and then we can check with our target function, right? We can query our friend, hey, did you really like this drink or not?
So concept learning is this idea of learning a Boolean valued function over all of the data instances. So we have our data instances down here, our capital X, And we're trying to learn the function output over that, and that's going to be our y. So we're going to separate this off and say this is our y value, okay, which is a function hidden from us over the data instances, okay? And each of the x's is going to comprise of here 6 different input attributes. So I have drink, which is takes 2 values. It's a binary valued attribute, either coffee or tea. Okay, milk, which takes 3 values, but we've only illustrated 2 here. C, which is evaporated milk. O, which means black, and another version, which is just plain without any modifier, and that means condensed milk. Okay, sugar we're going to denote as only having 2 values, either kosong meaning 0, no sugar at all, or gadai meaning extra sugar. Okay, iced, even, and in this case all of these things are iced, and the strength either gao meaning strong or po meaning weak, and the drink either to have here, which is nim for drinking, and tabao for taking away. Okay, so this is a case of supervised learning as we introduced in our concepts, our paradigms of machine learning that we talked about last time. And note, importantly, that everything in this problem is a discrete instance, right? Our Boolean function is discrete, as well as the training instances all have discrete values for their attributes. So when we want to represent some hypothesis H, there are actually many different choices that we can make. And the learner has to decide, or the algorithm that we're going to use is going to choose a specific hypothesis representation. And we're going to see over the course of this course that there's a large trade-off between the expressive power of the hypothesis space versus one that's smaller. So the more expressive you have, the more possible hypotheses there are. That means that the space gets larger and we have more possibilities to search from, which makes the problem more challenging. Okay, so today we're just going to consider a very simple representation where the hypothesis is basically a conjunction of simple constraints on each of the input attributes. So I can say, for example, for this one here, for the attribute of strength, I can either specify a particular value and say the strength of the drink must be strong or gao, or I can say it doesn't matter, I don't have a specific preference, or I can say that there's no value allowed at all. Okay, so strength equals no, which means I don't accept any drink that has any setting for that attribute. Okay, and so for example, this becomes a particular hypothesis for this concept, right? We can say that maybe we think our target function, our friend, likes drinks with evaporated milk or C, likes drinks that are iced, and always likes to prefer to drink here, but doesn't really care about whether they're drinking tea or coffee, whether it has sugar or not, and whether the drink is strong. So to do the concept learning task of enjoying drinking, we're going to have to give the learner a couple different things. We're going to have to give it the data instances, and like we said, here in this case we have 6 attributes, all of which take Boolean binary values rather, except for the one for milk, which has 3 different ones. So this one has evaporated milk, condensed milk, which doesn't have any words associated with it. You just order it without any modifiers, and O for black. Okay, so we have 3 value, let me take that out. 2 values, 3 values, 2 values, 2 values, 2 values, and 2 values for the possible settings for a particular drink. So each instance X is going to have to take on one attribute value for each of these attributes. We also have to give the hypothesis space, right? So here we've said that we're going to use a conjunction of constraints as a way of doing that. And we're going to say that an input instance here that we might get in our data set has to be drawn from the space of all possible drinks, any combination of them, even ones that are not in our data set, okay? When the hypothesis returns a positive value, that means we think we think the target function or friend likes the drink um, when it comes up as a 1. Okay? In other words, our hypothesis classifies that particular drink as a positive example, then we're going to say that that X is satisfied. We'll also need the unknown target concept, so we have to have access to actually the values of the f function. That's our y's, okay? So here it's going to be 0 or 1, or don't enjoy, or enjoy, okay? Or, and we're going to need noise-free training examples, right? All of the data set values so that we can get these instances. We'll need the function values, okay, the y's as well as the x's, right? And what our goal is to determine a hypothesis that's consistent with our data set, right? And what do we mean by consistency? Well, that's pretty simple, right? We're going to say a hypothesis is consistent with the set of training examples if and only if the hypothesis replicates the judgments of our target concept for all of the ones in our data set, okay? So, we might be asking ourselves, well, we introduce consistency on this side. That means that we have the same values as the target function for the data examples, right, that our hypothesis generates. So how is this different from saying that X satisfies on the last slide hypothesis H, right? So that has to do with just positive instances. And what's the implication of that? So just to make it clear, when we're talking about conjunctive hypothesis, what we mean is that we have to take the conjunction of all constraints on all of the 6 attributes. And these are going to be what we're going to denote as the hypothesis space for our current concept learner, okay? So our conjunctive learning algorithm that we've specified shortly is going to have to assume that the target concept actually falls within that space, so that our friend that we're trying to elicit drink preferences from actually has a target concept that can be represented as a conjunction of constraints. If we don't have that, for example, if they like certain drinks like tea with certain constraints and like other drinks like coffee with a different set of constraints, in other words, the disjunctive case, then our target concept would fall outside of that space, and we won't be able to represent it within the concept hypothesis space, okay? So we're going to see that a whole bunch of learners that we might choose from have to make some type of commitment in creating their hypothesis space, and it's going to create this type of border in the space of all possible hypotheses and just narrow down to ones that it thinks is likely, okay? So let's try to unpack this idea of the inductive learning assumption. Here we're saying that we believe that a hypothesis that is trained to replicate the target concept over the training data, that means over set D here, is going to be the best possible hypothesis that we could generalize for even unseen examples, meaning unobserved test cases, right? But if you think about that, that doesn't necessarily hold, right? We don't know anything about the testing set. So how can we say that whatever concept that we're trying to learn through our hypothesis is actually going to replicate well on an unseen data set? We can't actually say that. But without any other type of information, we are going to have to assume this. We have many different hypotheses that we could possibly generate, and the best one that we could generate so far against the training data is one that is going to approximate F well, meaning be consistent on the training data set. So let's unpack that a little bit more, right? So the learning task of our system is to determine an H that is going to approximate F as best as we can. And it has to do so over all possible instances X, okay? script X, right? Meaning all of the space of possible inputs. So any type of drink with those 6 values, or any type of image and that we would have from lecture 1, we would have to decide whether the person likes it or not, or whether that's a cat or a dog, for example. But really, the only information that we get about the true target function is its value over on a very limited set of data, usually just a training set, or X, capital X. And so what we can only do is basically guarantee how we can perform on that training data, right? If we can approximate H2F over the training set D, then that's pretty much the best that we can do, right? So we're just making this high assumption. It's not necessarily true that any hypothesis found to approximate the target function well on the training data set. We're just going to assume that that's going to generalize to the unobserved test examples.